Why didn't Jupiter become a second sun? Simply put, it just didn't have the mass. Without enough material to ignite nuclear fusion, Jupiter could only quietly radiate the leftover heat trapped deep inside. But that raises an intriguing question. Where does all that internal heat come from? And who, or what, is in charge of controlling its wildly chaotic atmosphere? Today, we're heading straight to Jupiter to peel back the layers beneath its dazzling skin and uncover the mysterious forces at play. Up close, Jupiter's face looks like a shattered mirror, splintered into streaks of brilliant cloud bands. Brownish belts and pearl-white zones spread out like ribbons, spiraling along the equator. But these aren't just decorative stripes. They're the very scars of powerful jet streams carving their way through the atmosphere. High-speed winds whip around the entire planet like raging dragons, organizing the atmosphere into alternating bands that stretch from the equator to the poles. These zonal jets crisscross east and west, each layer moving in the opposite direction of its neighbor. In the brighter zones, ammonia ice clouds rise from deep within, catching sunlight and glowing in white and golden hues. In the darker belts, we catch glimpses of deeper atmospheric layers, stained rust red and amber by compounds like ammonium hydrosulfide. Each band flows in the opposite direction of the one beside it, like a colossal painting sculpted by storms and turbulence. And the winds here? They reach speeds of several hundred kilometers per hour, far beyond the fiercest hurricanes on Earth. In Jupiter's upper atmosphere, jet streams can scream along at over 650 kilometers per hour. Thanks to the Coriolis effect generated by the planet's rapid rotation, Jupiter's entire atmosphere is torn into bands of high-speed, counter-rotating flows. Between these jets are alternating bright and dark bands that form silky patterns, like giant ribbons wrapped around the planet. The atmosphere is divided into a series of convection cells, each filled with rotating, rising warm air and sinking, cooling gases. The internal heat left over from Jupiter's formation powers this deep convection, constantly injecting energy into the wind bands and fueling an endless atmospheric ballet. Though the boundaries between jets are sharply defined, they're also violently unstable. Turbulent air masses collide and twist along these borders, creating waves and spirals in the clouds. Ammonia and water vapor surge upward from the depths, condensing into brilliant white cloud bands. In contrast, where air sinks, the skies grow clear and transparent, revealing the deeper, darker layers of Jupiter's alien atmosphere. All of Jupiter appears like a swirling piece of colored marble, boiling and spinning in silence. And hidden among its endless bands of clouds is one of the most legendary storms in the solar system, the Great Red Spot. This massive, oval-shaped crimson vortex has been raging in Jupiter's southern hemisphere for centuries. It's so vast it could swallow the entire Earth whole. Technically, the Great Red Spot is an anticyclonic system, a high-pressure storm spinning counterclockwise and rising far above the surrounding cloud tops. As you draw closer, you'll see its dense, elliptical cloud layers spiraling tightly together, their hue resembling weathered bricks. A layer of red haze drifts high above, cloaking the storm in a mysterious blood-red veil. To this day, scientists still don't know exactly what gives the spot its color. It could be complex organic molecules or phosphorus-rich compounds dragged up from deep below. Within the vortex, cloud bands and spirals wrap together like the iris of a colossal eye, endlessly turning. The outer winds rage at speeds of up to 430 kilometers per hour, and the fierce wind shear sculpts the cloud layers into surreal and dreamlike shapes. Ever since it was first observed over 150 years ago, the Great Red Spot has captivated scientists with its enduring power and beauty. White ammonia ice clouds tumble at its edges, being pulled into the storm's depths. Occasionally, smaller storms attempt to intrude. Some are flung away, while others are swallowed whole. The Great Red Spot not only dominates its own domain, but also disturbs the surrounding weather patterns from a distance. Yet in recent years, scientists have noticed that this roaring giant is shrinking. Its diameter is now only half of what it was at its peak. Despite this contraction, it remains the largest storm in the entire solar system. It completes a full rotation approximately every 6 Earth days. Interestingly, The storm's center is somewhat calmer than its roaring outer bands. Hovering above this towering pressure fortress is a red, misty crown, clearly separating the storm from the bright bands of clouds that encircle it. Occasionally, lightning flashes silently within its deep cloud layers, piercing the Jovian night with sudden bursts of brilliance. Data from NASA's Juno spacecraft suggests the storm may not be as deep as once imagined, but it still towers tens of kilometers above surrounding clouds, like a gaseous mountain rising from Jupiter's vast atmospheric ocean. And the Great Red Spot is not alone. Jupiter is almost entirely covered with smaller storms and vortices. If you follow the cloud bands closely, you'll spot chains of faint white ovals. These are miniature anticyclonic storms, spinning counterclockwise just like the Great Red Spot. These smaller storms are essentially miniature versions of the Great Red Spot, just far more modest in size. Some of them can last for decades, while others flicker into existence only to vanish within days. Take the year 2000, for instance. 3 white oval storms merged into a larger one, which was later named Oval BA. Over time, it turned red, earning it the nickname Red Spot Jr. At its peak, it reached about half the size of the Great Red Spot. Between these storms, high-speed jet streams stretch and twist the atmosphere into elongated vortex bands, forming rippling distortions at the boundaries between light and dark regions. Some of these waves even take the shape of Kelvin-Helmholtz instabilities, wave-like patterns created when airflows at different speeds shear past one another. In certain areas, you might spot dark, boat-shaped clouds drifting slowly in the currents. Elsewhere, bright, popcorn-like cloud clusters rise up, signaling intense convective storms surging skyward. Because Jupiter lacks a solid surface to interrupt them, these storms can plunge deep into the planet's atmosphere and persist with remarkable longevity and ferocity. Gazing along Jupiter's vast curvature, you'll witness a breathtaking spectacle. From tiny vortices just a few hundred kilometers wide to colossal turbulence zones where multiple storms crash and swirl together in atmospheric chaos. This is especially dramatic behind the Great Red Spot, where disrupted airflows form a storm nursery, filled with eddies and pale clouds. It's here that new small storms are born. Yet even amid all this surface turmoil, there's an underlying order. Each storm is locked tightly within its own latitude band, confined by powerful jet streams. None of them stray outside their atmospheric lanes. If you were to fly over Jupiter's poles, the view would be nothing short of breathtaking. At the North Pole, 8 gigantic polar cyclones encircle a central vortex, forming an almost perfect octagon. Each cyclone spans between 500 and 2,800 kilometers across. They press against each other in close proximity, yet spin independently in a stunning display of balance, as if guided by some invisible force. Each cyclone rotates counterclockwise, their spiral arms interwoven but never chaotic. It's like watching a masterwork of geometric elegance unfold in the sky, a superstructure sculpted by nature itself. At the South Pole, a similar marvel takes place. Originally composed of 5 massive cyclones orbiting a central vortex, the system later grew to 6, forming a nearly perfect hexagonal pattern. These polar storms have persisted for years with virtually no significant distortion, hinting at some hidden, stable physical mechanism. Perhaps it's the intricate fluid dynamics between vortices, or the strong polar jet streams that hold the entire system in place. And just as you begin to lose yourself in this symmetrical polar ballet, Jupiter plays another card: lightning. A bright flash tears across the polar night, illuminating the cloud tops in a burst of silver. This is no ordinary lightning. It's an explosion of raw energy. Thunderstorms on Jupiter are far more powerful than anything we see on Earth. These bursts are the signatures of titanic electrical storms powered by deep convection and Jupiter's immense energy reserves. As early as 1979, NASA's Voyager spacecraft captured brief but brilliant flashes high in Jupiter's atmosphere, marking humanity's first glimpse into the electric secrets buried within the chest of this gas giant. At the time, scientists believed that lightning on Jupiter could only occur deep within its water cloud layers, where temperatures were moderate and conditions similar to Earth's thunderstorm zones. But as the Juno mission delved deeper into Jupiter's atmosphere, a stunning revelation emerged. Jupiter also hosts high-altitude lightning. These flashes ignite in the frigid upper layers of the atmosphere, where temperatures plunge to -88°C, far below the freezing point of water. Under normal circumstances, any water would be frozen solid. But on Jupiter, ammonia acts as a natural antifreeze, allowing moisture to exist in a bizarre semi-liquid state, even in these icy heights. During intense storms, chunks of electrified ice are hurled more than 24 kilometers into the upper atmosphere, entering a freezing zone saturated with ammonia. There, the ice begins to melt and partially evaporate, mixing with the ammonia gas to form a muddy, slushy hybrid known as mushballs. These exotic spheres tumble through the clouds, rubbing violently between ice crystals and electrified particles, building up static charge. Eventually, the tension releases in shallow lightning bursts, a symphony of electrical fire echoing through clouds where ammonia and electrified ice collide. These lightning strikes briefly illuminate the upper skies in eerie flashes of blue and gold. Juno's cameras, observing Jupiter's night side, captured these breathtaking moments. Though each strike lasts only a few milliseconds, their energy rivals some of the most powerful lightning strikes on Earth. Deeper within Jupiter's atmosphere, roughly 48 to 64 kilometers below the cloud tops, traditional thunderstorms still rage. Here, water exists in all three states: ice, liquid, and vapor, creating chaotic conditions much like those found inside Earth's cumulonimbus clouds. The violent separation of electrical charge spawns bolts of lightning far more energetic than anything Earth has to offer. Juno has detected tens of thousands of these discharges, each emitting sharp radio signals known as whistlers that echo through Jupiter's magnetic field and into the depths of space. Even more remarkably, the discovery of these shallow lightning bolts helped solve a long-standing scientific mystery. Why is ammonia mysteriously missing from Jupiter's upper atmosphere? As it turns out, the mushballs formed from ammonia and ice are quietly ferrying the gas downward into the depths of the atmosphere, hiding it from detection. After each thunderous eruption, another flash cuts through the distant cloudscape, casting light across the towering convective cloud pillars. Driven upward by the internal heat pulsing through Jupiter's core, these cloud towers soar to heights of over 30 kilometers. For a fleeting moment, lightning outlines their massive forms, like cosmic hammers forging Jupiter's atmospheric world. If Jupiter's clouds and storms paint a wild and majestic portrait across its surface, then its auroras are the crown's most dazzling jewels. At both of Jupiter's poles, the auroras blaze with astonishing energy, radiating deep blue and violet light, like the most brilliant gems in a celestial kingdom. Unlike Earth's auroras, which flicker to life only during periods of intense solar wind, Jupiter's auroras almost never turn off. Their power is staggering, hundreds of times stronger than Earth's, continuously draping the polar regions in an electric cloak of glowing light. These auroras aren't just driven by the solar wind. Jupiter's own colossal magnetic field plays a vital role as well. Its magnetic strength is between 16 and 54 times that of Earth, generated by a deep, rotating layer of metallic hydrogen within the planet. This immense magnetic field captures high-energy particles from the surrounding space and funnels them toward the poles. When these particles slam into Jupiter's upper atmosphere, they excite hydrogen molecules, releasing ultraviolet and infrared light and forming immense, glowing rings of aurora. In enhanced imaging, Jupiter's northern aurora spirals like an electric blue vortex, swirling and dancing under the guidance of magnetic lines. Even more fascinating, Jupiter's moons are active participants in this auroral spectacle, especially Io, the most volcanically active moon in the solar system. Constant eruptions on Io spew ionized sulfur and oxygen into space, feeding Jupiter's magnetosphere with fresh energy. As Jupiter rotates, these charged particles are whipped toward the poles by the magnetic field, further igniting the auroral displays. Io's path through the auroral ring leaves a bright footprint, a glowing mark at the edge of the northern aurora, like a tiny torch illuminating the invisible bond between moon and planet. And Io isn't alone. Europa and Ganymede also leave subtle traces of their passage, contributing to the magnetic choreography. Sometimes when the sun erupts and sends powerful particle storms racing across space, they crash into Jupiter's magnetic field and supercharge the auroras. For a brief moment, the polar light shows surges leaping thousands of kilometers high, far outshining anything Earth's skies have ever seen. But don't forget, even if you stood hovering above Jupiter's poles, you wouldn't actually see this spectacle with your own eyes. Most of the auroral light is emitted in ultraviolet and X-ray wavelengths, far beyond human vision. Jupiter's auroras are not just visual wonders. They are a breathtaking electromagnetic ballet, the most powerful of their kind in the solar system. And now let's pull back, away from Jupiter's blazing auroras and storm-racked cloudscape, and look outward into the vast reaches beyond. There is still one more hidden wonder awaiting discovery: Jupiter's rings. Yes, Jupiter has rings too. But unlike the radiant, iconic bands of Saturn, Jupiter's rings are faint. So delicate they resemble gossamer threads suspended in space. They weren't even discovered until 1979. Unlike Saturn's dazzling rings, Jupiter's are slim, sparse, and almost entirely transparent, visible only when backlit by the sun. In images, a slender main ring appears as a glowing filament encircling the equator. Beyond it lies a faint, ghostly halo, wispy ring arcs extending into space. These fragile structures owe their existence to Jupiter's small inner moons, particularly Amalthea and Adrastea, which appear as faint pinpricks of light near the ring plane. These tiny moons are constantly bombarded by micrometeoroids. Each impact throws up dust, flinging tiny grains into orbit. Over time, this ejected material accumulates, forming the subtle ring system we see today. Adrastea, only about 19 kilometers in diameter, is the primary source of material for the main ring. Slightly farther out, moons like Medes and Amalthea contribute additional dust, feeding the planet's broader outer ring structures. Up close, the particles in these rings are astonishingly small, mostly silicate fragments on the micrometer scale. Dull and non-reflective, they're nearly invisible in visible light. Only through infrared imaging or perfectly angled backlighting can we glimpse their elusive presence. So what kind of world is Jupiter? When you take it all in, its ever-churning atmosphere, its blazing internal heat, its thunderous storms, its auroras piercing the night sky, its nearly invisible rings of dust, and its retinue of moons, Jupiter emerges as more than a planet. It is a dynamic system, a cosmic symphony in motion. Jupiter is a king, burning with energy in a state of eternal transformation. It defies summary. No matter how we describe it, it remains the same ancient giant, etched with the primal scars of creation. To this day, deep in the ocean of stars, it continues to tell an unfinished story, one written in thunder, light, and the raw breath of the universe itself.